Hello, young physicists. Last time we dealt with displacement, change in place, and how that's different from the distance traveled. Right? Displacement was a change in a distance that we define as a final point minus an initial point. We're going to take that a step farther today with the definition of velocity. So, velocity has two flavors, so to speak. There's an average velocity and an instantaneous. As you probably guess from the words, at a particular instant velocity, and this is an average over time. We're going to start looking at average velocity. Now, first, velocity is a vector. We talked about vectors last time. The vectors have magnitude and direction and units. That's different than speed, which only has magnitude. Right? So, if you're driving 65 miles an hour north on the thruway, that's your velocity. If you're driving 65 miles an hour on the thruway, that's your speed, because you have not provided a directional component. So average velocity, V for velocity, and since we're one dimension, we're saying x. So this is motion along. It's defining motion along the x-axis. Putting a bar over this for average. That's the book's notation for average. This can get confusing because commonly when you write vectors, you put a bar. For vectors, I'm going to put a bar and an arrow to try to work that out. And I think you can get most of that from context. So, average velocity is the displacement. Is how much of a displacement occurred in a certain period of time. The dimensions are going to be length over time. Meters per second, miles per hour, that sort of thing. So, notice this delta x, average velocity, only cares about the starting and ending values of velocity, not the path taken. Okay, does not matter. So if you go from here to here in the same amount of time, you're going to end up with the same average velocity if you do this or if you do this. Right, because your final point and your initial point are the same, whether you took the red line or the blue line, and we're saying that if you did that in the same amount of time, change in x over change in time is the same. Obviously, you're traveling faster, at least most of the time, on the blue line, but your average velocity is the same. Okay, so let me clean this up a little bit so I can have a little more space for the next thing. I'm going to draw a graph that hopefully the picture will help to solidify the difference. So this is time, the x-axis here. This is displacement, and they're both increasing. So if you have an x2 and an x1, the change between them is delta x. If you have a t1 and a t2, the change from one to the other is a delta t. Right, so let's take some path. There are some path that goes from here, point 1 to point 2. Point 1 at x1 at t1, point 2 is at x2 at t2, and the thing goes something like this. Alright, so average velocity, the average velocity is going to be the slope of that line connecting them. That average velocity is the change in x over the change in t. Right? From x2 to x1, the change in x is here, change in t is here. That's your average velocity. So, if we were to just draw the right triangle here. Okay, it's the slope of the hypotenuse of that triangle. Okay, now, as I said before, speed and velocity are not the same in physics. Sometimes we want speed. So, average speed equals total distance divided by total time. Notice there's no direction here. Okay, this is all magnitude. This is the same unit of velocity, but this is a scalar quantity. Okay, it has only magnitude and units. It is not a vector quantity. It does not have direction. Okay. So, that's the difference between average speed and average velocity. Now, I said there was a second kind of velocity, and that is instantaneous velocity. The velocity at some particular point of time, right? Some exact point of time. So we define that as the limit as delta t goes to 0 of the change in x over the change in t. It's still change in x over change in t, but it's now gone down as this time change. The time interval diminishes to near 0. And in the limit, it goes to our differential form. So this is our instantaneous velocity. Alright, so this is, if we look at this mathematically, it's the derivative, the time derivative of displacement. So if you have a mathematical description of the displacement of a particle, taking the derivative of it gives you the instantaneous velocity. Okay, so graphically, if you draw this, and I don't want to crowd that one up there, and draw some other line. The instantaneous velocity is the tangent line to the curve at any particular point. This is instantaneous velocity at t2. Okay, so, and just as with average speed, the instantaneous speed is the magnitude of the velocity, right? Because speed is just magnitude. All right, so let's mess with this a little bit. So we have a particle for which we have a mathematical description of its displacement. So the particle moves according to this expression. X is minus 4 times time plus 2 time squared, where x is in meters, t is in seconds. We are asked to find the displacement of the particle and we're going to have another A here, big A, from t equals 0 to t equals 1. Part B of this, from t equals 1 to t equals 3. Alright, so let's do this. A, okay, we have the equation up here. So x, I'm going to call this x0, because it starts at 0. It's going to equal minus 4 times the time at 0, which is 0, plus 2 times the time at 0, which is 0. So that all equals 0. X at 1 equals minus 4, 1 second plus 2 times, oh, that's supposed to be squared, times 1 second squared. So this is just going to be 2, that's going to be minus 4. Minus 4 plus 2 is minus 2. So, taken together, the change in x from 0 to 1, so, and we're going to call that delta x 0 to 1, the change in displacement from 0 to 1, equals x1 minus x0. So that equals minus 2 minus 0 equals minus 2 meters. Or B. We're going now from T1 to T3. So we already have x1, x at T1, so that's minus 2. So now we're going to find x3, that's minus 4 times the time of 3, plus 2 times 3 squared. And that works out to, let's see, 3 times 3 is 18. So that's minus 12 plus 18. So that comes out to 6 meters. Now, delta x, going from 1 to 3, is going to equal the final minus the initial. 3 is the final. So it's going to equal x3 minus x1. That's the displacement. So that's 6 minus a minus 2 equals 8 meters. Okay. Same problem. I erased it, but you have all the problem information. B. We're going to calculate the average velocity during each interval. So, part A, delta x over delta t. So, delta x from above, delta, well, you should be specific about this. This is delta x 0 to 1, delta t 0 to 1 equals minus 2, we found that before, and going from 0 seconds to 1 second is 1 second. So the average velocity here is minus 2 meters per second. Velocity average. Part B, exactly the same thing. Average velocity for this one is going to be x 1 to 3 over, delta x, delta t 1 to 3. We found this one, delta x, to be 8 meters. 3 minus 1 is 2, so 2 seconds of traveling time. So that gives us, we don't need the positive sign, but just to make the point, 4 meters per second. And lastly, part C, we want to calculate the instantaneous velocity of this particle at a time of 2.5 seconds. Alright, now, remember, velocity, instantaneous velocity, was defined as a derivative of the displacement function with time So that's going to be the derivative of the function we were given in the beginning. Remember, x equals minus 4t plus 2t squared. So we substitute in minus 4t plus 2t squared, and take the derivative of that, ends up being minus 4. 2 times 2 is 4 plus 4t. And at 2.5 seconds, you just plug in 2.5 into the t here, and you end up with an instantaneous velocity. And sometimes this is written like this. The velocity at 2.5 seconds is going to be minus 4 plus 4 times 0.25. And that ends up being 6 meters per second. Not 0.25, 2.5. 2.5. Okay. Okay, that's it for velocity. We'll see you next time around when we dive into acceleration. Till then, bye-bye.